Right now, somewhere in our galaxy, there is an object so dense, so violently compressed, that the very atoms inside it have been completely destroyed. Not broken apart, not rearranged, destroyed. The fundamental building blocks that make up everything you have ever touched, everything you have ever seen, everything you are, simply cannot exist inside this object. Atoms, the structures that have survived for billions of years, that have endured the heat of stars and the cold of deep space, that form every element on the periodic table, cannot hold themselves together under the pressure found inside a neutron star. The force crushing matter inside these objects is so extreme that it overwhelms the very laws that give atoms their structure and their identity. And what replaces ordinary atomic matter is something so strange, so alien, that physicists are still fighting to understand what it truly is. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Everything you have ever touched is made of atoms. The chair you are sitting in right now, the air filling your lungs, the screen you are looking at, your own skin, your bones, the blood moving through your veins, all of it is atoms. And those atoms are remarkably, almost stubbornly, durable. They survive things that would obliterate anything humans have ever built. They endure temperatures of millions of degrees inside the cores of stars. They withstand the crushing pressure at the center of planets. They shrug off bombardment by cosmic radiation that has been streaming through the universe for billions of years. The atoms in your body right now are ancient. Many of them were forged inside stars that exploded long before our solar system even existed. Some of the hydrogen in the water you drank this morning has been around since the first few minutes after the Big Bang, roughly 13.8 billion years ago. These atoms have survived everything the universe has thrown at them. They have persisted across almost the entire history of the cosmos. So when I tell you that inside a neutron star, atoms cannot survive, that they are utterly and completely destroyed, I need you to understand how extraordinary that claim really is. The conditions inside these objects overwhelm the very forces that have held atoms together for billions of years. The fundamental architecture of matter itself collapses. And to understand how that happens, we first need to understand what an atom actually is, what holds it together, and why it is normally so resilient. Let's start with the basics, and I mean the real basics. Not the simplified version you might remember from school, but the actual physics of what makes an atom an atom. An atom is the smallest unit of a chemical element that retains the identity of that element. A gold atom is gold. A carbon atom is carbon. An oxygen atom is oxygen. If you break an atom apart into its components, you no longer have that element. You have something else entirely. You have subatomic particles, pieces that no longer carry the chemical identity of the original element. The periodic table, that chart hanging on the wall of every chemistry classroom in the world, is really a catalogue of atoms. Each box on that table represents a different type of atom with a different number of protons in its nucleus. Hydrogen has 1 proton. Helium has 2. Carbon has 6. Iron has 26. Uranium has 92. The number of protons defines the element. Change the number of protons, and you change what the element is. That number is the atom's identity card. Every atom has the same basic structure. At the center is the nucleus, a dense core made of protons and neutrons packed tightly together. Protons carry a positive electrical charge. Neutrons carry no charge at all. They are electrically neutral, which is where their name comes from. Surrounding this nucleus, at relatively enormous distances compared to the size of the nucleus itself, are electrons. Electrons carry a negative electrical charge, exactly equal in magnitude to the proton's positive charge, but opposite in sign. In a neutral atom, the number of electrons equals the number of protons, so the charges balance out, and the atom as a whole has no net charge. Now here is something that most people find genuinely surprising when they first hear it. An atom is almost entirely empty space. The nucleus, where almost all of the atom's mass is concentrated, is extraordinarily tiny compared to the atom as a whole. If you could scale an atom up to the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. The electrons would be like tiny gnats buzzing around somewhere in the upper seats. Everything in between is empty. Nothing. Just space. The solid world you experience around you, the table you can knock on, the floor holding you up, all of it is overwhelmingly made of nothing. When you touch a table and feel something solid, you are not actually touching the atoms in the table. Your hand's atoms never make contact with the table's atoms. What you feel is the electromagnetic force, the repulsion between the electron clouds in your hand and the electron clouds in the table pushing against each other. The sensation of solidity is an electromagnetic illusion. It is the force that creates the experience, not physical contact between particles. This brings us to the first critical point. The electromagnetic force is the architect of the atom. It is the force that gives atoms their structure, their size, their shape, and their behavior. Without the electromagnetic force, atoms could not exist. Here is how it works. Protons in the nucleus carry a positive charge. Electrons carry a negative charge. Opposite charges attract each other. So the positively charged nucleus pulls the negatively charged electrons toward it. This attractive force is what keeps electrons bound to the atom. It is the glue holding the whole structure together. If you tried to rip an electron away from an atom, you would have to put energy in to overcome this electromagnetic attraction. The closer the electron is to the nucleus, the more tightly it is bound, and the more energy you need to pull it free. But if the nucleus is pulling electrons toward it, why don't the electrons just crash into the nucleus? In classical physics, they should. A negatively charged particle attracted to a positively charged nucleus should spiral inward and collide with it in a fraction of a second. This was actually one of the great mysteries of physics in the early 1900s. The model of the atom proposed by Ernest Rutherford in 1911, based on his famous gold foil experiment, placed electrons orbiting a dense nucleus like planets around the Sun. But according to the electromagnetic theory developed by James Clerk Maxwell, an orbiting electron should radiate energy as it accelerates around the nucleus. Losing energy means spiraling inward. Every atom in the universe should collapse in about 100 trillionths of a second. Obviously, that doesn't happen. Atoms are stable. Matter exists. You exist. So something else must be going on. The answer came from quantum mechanics, a revolutionary framework that emerged in the early 20th century and completely overturned how we understand the behavior of particles at the smallest scales. In 1913, Niels Bohr proposed a radical idea. Electrons don't orbit the nucleus in just any path. They can only exist at specific energy levels, like steps on a staircase. An electron can be on step 1 or step 2 or step 3, but it cannot be between steps. There is no step 1.5. These energy levels are quantized, meaning they come in fixed, discrete amounts. An electron can jump from one level to another by absorbing or emitting energy, but it cannot smoothly spiral inward. There is a lowest possible energy level called the ground state, below which the electron simply cannot go. This is why atoms don't collapse. The electron reaches the ground state and stays there. It has nowhere lower to fall. This was expanded and formalized through the 1920s by physicists including Erwin Schrödinger, Werner Heisenberg, and Paul Dirac. Quantum mechanics revealed that electrons are not tiny balls orbiting the nucleus like miniature planets. They exist as probability clouds, wave functions spread out in space, describing the likelihood of finding the electron at any given location. These probability clouds have specific shapes depending on the energy level. Some are spherical, some are dumbbell-shaped, some are more complex. But in every case, the electron occupies a defined quantum state with a specific energy, a specific angular momentum, and a specific orientation. And now we come to one of the most important principles in all of physics, a rule that is absolutely essential to understanding why atoms have the structure they do and why matter behaves the way it does. This is the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. The Pauli exclusion principle states that no two electrons in an atom can occupy the same quantum state simultaneously. Each electron must have a unique set of quantum numbers. Think of it like assigned seating. Every seat in the atom has room for exactly one electron with a specific set of quantum properties. Once a seat is taken, no other electron with the same properties can sit there. It must find a different seat. This principle is the reason the periodic table looks the way it does. It is the reason different elements have different chemical properties. It is the reason atoms stack electrons into shells and subshells, filling up lower energy levels first, then moving to higher ones as more electrons are added. Hydrogen has one electron in the lowest shell. Helium has two, filling that first shell completely. Lithium has three, so the third electron must go into the next shell up, because the first shell is full. This layered structure gives each element its unique chemical behavior. Carbon bonds differently from oxygen, which bonds differently from iron, which bonds differently from gold. All because of how the electrons are arranged, and the electrons are arranged the way they are because of the Pauli exclusion principle. Without this principle, all electrons would collapse into the lowest energy level, piling on top of each other in the ground state. Every atom would have the same size and the same chemical properties regardless of how many electrons it had. There would be no chemistry, no molecules, no water, no proteins, no DNA, no life. The Pauli exclusion principle is not just a rule of quantum mechanics. It is the foundation of atomic structure, and therefore the foundation of everything that exists. But there is another force at work inside the atom, one that operates at a much smaller scale. The nucleus itself requires an explanation. Protons carry positive charges, and like charges repel each other. If you pack multiple protons into a tiny space, they should push each other apart with tremendous force. The electromagnetic repulsion between protons in a nucleus is enormous. Two protons separated by the width of a nucleus are pushing against each other with a force of roughly 20 pounds. That might not sound like much, but remember, these are subatomic particles. The force relative to their size is staggering. So what holds the nucleus together? Why doesn't it fly apart? The answer is the strong nuclear force, one of the four fundamental forces of nature. The strong force is the most powerful force in the universe, but it operates only at extremely short ranges, roughly the diameter of a nucleus or smaller. Beyond that distance, it drops off to essentially zero. Within the nucleus, though, the strong force is about 100 times more powerful than the electromagnetic repulsion between protons. It acts like incredibly powerful glue, binding protons and neutrons together into a dense, stable core. Neutrons play a crucial role here. They add to the strong force attraction without adding electromagnetic repulsion because they carry no charge. In heavier elements, you need more and more neutrons to stabilize the nucleus against all those protons pushing against each other. This is why heavy elements like uranium have significantly more neutrons than protons. So let's take stock of what an atom requires to exist. First, it needs the electromagnetic force to bind electrons to the nucleus, creating the electron cloud that defines the atom's size and chemical properties. Second, it needs quantum mechanics, specifically the rules governing energy levels and the Pauli exclusion principle, to prevent electrons from collapsing into the nucleus and to give each element its unique identity. Third, it needs the strong nuclear force to hold the nucleus together against the electromagnetic repulsion between protons. These three ingredients, the electromagnetic force, quantum mechanical rules, and the strong nuclear force, are what make atoms possible. They are the architecture of matter. And this architecture is extraordinarily robust. Atoms are not fragile. They do not break easily. Consider what atoms survive on a daily basis right here on Earth. The nitrogen and oxygen atoms in the air around you are constantly colliding with each other at speeds of several hundred meters per second. These collisions happen billions of times every second, and the atoms survive every single one. They bounce off each other, their electron clouds repelling, and they continue on their way completely intact. The atoms in the rocks beneath your feet have survived for billions of years, enduring volcanic eruptions, tectonic collisions, extreme pressures deep underground, and bombardment by cosmic rays from space. They are still atoms, still intact, still carrying the same number of protons they have always had. But the real testament to atomic resilience is what happens inside stars. Right now, in the core of our Sun, hydrogen atoms are being subjected to temperatures of about 15 million degrees Celsius and pressures about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, atoms are stripped of their electrons completely. The nuclei are exposed, bare protons hurtling around in a plasma so hot that electrons cannot remain bound. And yet, the nuclei themselves survive. In fact, they do more than survive. They undergo nuclear fusion, where hydrogen nuclei smash together with enough force to overcome their electromagnetic repulsion and fuse into helium, releasing enormous energy in the process. This is what powers the Sun. This is what powers every star in the universe. And even in this process, while the nuclei are being transformed from one element into another, the fundamental structure of nuclear matter persists. Protons remain protons. Neutrons remain neutrons. The strong force continues holding nuclei together. Atoms in the outer layers of the Sun remain atoms, ionized and superheated, but structurally intact. Inside more massive stars, the conditions get even more extreme. Stars much heavier than our Sun reach core temperatures of billions of degrees during their final stages of life. They fuse heavier and heavier elements, building up layers like an onion, with hydrogen fusing in the outermost shell and progressively heavier elements fusing deeper in. Carbon fuses into neon and magnesium. Oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron. At each stage, the temperatures and pressures are higher than the last, and yet atoms persist. Nuclei survive. Even at billions of degrees and pressures that are beyond anything we can replicate on Earth, atomic structure holds. Iron is where stellar fusion stops. This is critically important and worth understanding. Every fusion reaction before iron releases energy. Fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. All the way up to iron, each step releases energy that helps support the star against its own gravity. But iron is different. Iron has the most stable nucleus of any element. Fusing iron into heavier elements does not release energy. It requires energy. It is an endothermic reaction. So when a massive star builds up an iron core, fusion can no longer provide the energy needed to hold the star up against gravity. The star has been fighting gravity its entire life, and iron is where it finally loses the ability to fight back. But we are getting ahead of ourselves. The point right now is that atoms, even under the most extreme conditions found inside the cores of the most massive stars in the universe, remain atoms. Their structure persists. The electromagnetic force continues to define electron behavior. the strong nuclear force continues to hold nuclei together. Quantum mechanics continues to govern how particles arrange themselves. The architecture holds. So what could possibly overwhelm something this durable? What force in the universe is strong enough to break something that has survived the cores of stars, the violence of supernova, the bombardment of cosmic rays, and billions of years of cosmic history? The answer is gravity. But not gravity as you experience it here on Earth. Not the gentle force that keeps your feet on the ground and makes apples fall from trees. I am talking about gravity concentrated to a degree that is almost impossible to put into words. Gravity scaled up to a level where it becomes the most destructive force in the universe. Here is what makes gravity unique among the fundamental forces. It is cumulative and it has no maximum. The electromagnetic force can be positive or negative, attracting or repelling. Over large distances, positive and negative charges tend to cancel each other out. Large objects are usually electrically neutral, so the electromagnetic force between them is negligible. The strong nuclear force is incredibly powerful, but extremely short-ranged. It operates only within the nucleus and has no effect beyond a few femtometers. Gravity, on the other hand, is always attractive. Every piece of mass in the universe attracts every other piece of mass. And unlike the strong force, gravity has infinite range. It weakens with distance, but it never reaches zero, it never switches off, and it never cancels out. This means that as you pile more and more mass together, the gravitational force at the center keeps growing. There is no upper limit. Add more mass, and gravity gets stronger. Add more still, and it gets stronger again. Every atom you add to a massive object contributes its mass to the total gravitational pull, and that pull acts on every other atom in the object. In a small object, like a rock or even a planet, gravity is significant but manageable. The electromagnetic forces between atoms in the rock are far stronger than the gravitational compression, so the rock holds its shape easily. Even inside Earth, where gravity has compressed rock and metal into a dense core reaching temperatures of about 5,400 degrees Celsius and pressures of about 360 billion pascals, atoms remain intact. Iron atoms in Earth's core are squeezed and heated, but they are still iron atoms. Their nuclei still have 26 protons. Their electrons still arrange themselves according to quantum mechanics, even if those arrangements are modified by the extreme pressure. The electromagnetic force and quantum mechanical rules still dominate over gravity at these scales. But stars are more massive than planets. Much more massive. Our Sun contains about 330,000 times the mass of Earth. Stars that are 8, 10, 20 or even 50 times the mass of the Sun exist throughout the galaxy. The more massive the star, the stronger the gravitational compression at its core, and throughout the star's life, this gravity is held in check by the energy produced through nuclear fusion. The outward pressure from fusion reactions balances the inward pull of gravity. It is a delicate equilibrium that can last for millions or billions of years, depending on the star's mass. But this equilibrium cannot last forever. The star eventually runs out of fuel, and when it does, when the nuclear furnace at the core finally goes dark, gravity wins. There is nothing left to push back, and when gravity wins in a sufficiently massive star, the collapse that follows is so sudden, so violent, and so complete that it crushes matter beyond anything the electromagnetic force can withstand. The gravitational energy released in this collapse is staggering. In a matter of seconds, the core of a dying star collapses from a structure thousands of kilometers across to a dense ball roughly 20 kilometers in diameter. The material at the center is compressed to densities that are hundreds of trillions of times the density of water. At these densities, atoms cannot exist. The electron clouds that define atomic structure are squeezed into the nucleus itself. The The empty space that makes up 99.99999999999% of every atom is violently eliminated. The electromagnetic force, which has faithfully held atoms together for billions of years across every environment in the universe, is simply overpowered. This is the threshold we are approaching. The point where the familiar rules of matter, the rules that govern everything you have ever experienced, everything you have ever touched, everything you are made of, simply stop working. Gravity does not care about the electromagnetic force's preferences. Gravity does not care about the beautiful architecture of electron shells and energy levels. When enough mass collapses into a small enough space, gravity overwhelms everything. And what is left on the other side is something completely alien. Something that is no longer made of atoms at all. This is what happens inside a neutron star. And understanding the specific mechanism, how exactly gravity destroys atoms and what replaces them, requires us to go deeper into the physics of collapse, into the strange quantum process that converts the building blocks of ordinary matter into something else entirely. A process where electrons and protons cease to exist as separate particles, where the periodic table becomes meaningless, and where matter enters a state so extreme that physicists are still working to understand its full nature. The architecture of the atom is extraordinary. It is robust, elegant, and has persisted across nearly the entire age of the universe. But it was built to withstand electromagnetic challenges, thermal challenges, and even nuclear challenges. It was not built to withstand the unlimited, relentless, ever-accumulating force of gravity compressed into a space smaller than a city. And when that compression comes, the architecture does not bend, it does not flex, it shatters completely, and something fundamentally new takes its place. To understand how gravity destroys atoms, we need to follow the sequence of events that leads to this destruction. It does not happen randomly. It does not happen everywhere. It happens under one very specific set of circumstances, inside the collapsing core of a massive dying star. And the physics that drives it is precise, measurable, and deeply strange. The destruction of atoms inside a neutron star is not simply a matter of crushing them. It is a fundamental transformation of matter from one state into an entirely different state, a transformation so complete that the original particles lose their individual identities. But before we get to the moment of destruction, we need to understand the last line of defense that atoms have against gravitational collapse. Because atoms do not go quietly, they fight back. And the weapon they use is one we have already discussed: quantum mechanics. Remember the Pauli exclusion principle from earlier? No two electrons can occupy the same quantum state at the same time. Each electron needs its own unique set of quantum numbers, its own seat in the atom. This principle does not just govern how electrons arrange themselves inside individual atoms. It also governs what happens when you try to compress matter to extreme densities. Imagine squeezing a collection of atoms together, packing them tighter and tighter. At first, the atoms resist, because their electron clouds repel each other through the electromagnetic force. This is ordinary pressure, the kind you experience when you compress a gas or squeeze a solid. But as you squeeze harder and harder, the atoms are forced closer together. The electron clouds begin to overlap. Electrons from different atoms are being pushed into the same region of space. And this is where the Pauli exclusion principle becomes critical. Because as the electrons are forced closer together, they start running out of available quantum states. The low-energy seats are full. The electrons are being crammed into a space where there simply are not enough unique quantum states for all of them at low energy levels. The only option is for electrons to occupy higher and higher energy states. And occupying higher energy states means moving faster. The electrons are forced to move at extraordinary speeds, not because anything is pushing them, but because quantum mechanics demands it. They cannot all be in the same state, so the only way to accommodate them is to put them in higher energy, faster moving states. This creates a pressure. Not the pressure of hot gas expanding, not the pressure of electromagnetic repulsion between atoms, but a uniquely quantum mechanical pressure called electron degeneracy pressure. It is the resistance of electrons to being squeezed into the same quantum states. It has nothing to do with temperature. You could cool the matter to absolute zero, and this pressure would still exist, because it comes from quantum mechanics, not thermal energy. Electron degeneracy pressure is what supports a white dwarf, the dense remnant left behind when a star like our Sun dies. When a star with a mass similar to the Sun exhausts its nuclear fuel, its core contracts under gravity. But the contraction is halted by electron degeneracy pressure. The electrons in the core resist further compression because the Pauli exclusion principle forbids them from being squeezed any tighter. The result is a white dwarf, an object roughly the size of Earth, but containing about the mass of the Sun. A teaspoon of white dwarf material would weigh about 5 to 6 tons on Earth. The density is extraordinary, roughly 1,000,000 times the density of water. But atoms still exist inside a white dwarf. They are crushed and stripped of their outer electrons, but the nuclei are still intact. The electrons are still present, still obeying quantum mechanical rules. The identity of elements is preserved. Iron is still iron. Carbon is still carbon. The periodic table still applies. Electron degeneracy pressure holds the line. But this defense has a limit. In 1930, a young Indian physicist named Subramanian Chandrasekhar, barely 20 years old, was travelling by ship from India to England to begin graduate studies at Cambridge. During that voyage, he performed a calculation that would change astrophysics forever. He asked a simple question. Is there a maximum mass that electron degeneracy pressure can support? Is there a point beyond which the electrons simply cannot resist gravity, no matter how fast quantum mechanics forces them to move? The answer was yes, and the limit he calculated was about 1.4 times the mass of the Sun. This number is now called the Chandrasekhar limit, and it is one of the most important numbers in all of astrophysics. Here is why this limit exists. As the mass of a white dwarf increases, the gravitational compression becomes stronger. The electrons are forced into higher and higher energy states, which means they are forced to move faster and faster. Chandrasekhar realized that as the electrons approach the speed of light, something changes in the physics. At speeds close to light speed, Einstein's special relativity modifies how particles behave. The relationship between energy and momentum changes. The pressure the electrons can provide no longer increases fast enough to keep up with the increasing gravitational force. There is a crossover point, a mass at which the electrons would need to exceed the speed of light to provide enough pressure to support the star. But nothing can exceed the speed of light. This is a fundamental law of physics, not a technological barrier. The electrons hit a wall. They cannot move fast enough. They cannot provide enough pressure. And if the mass exceeds 1.4 solar masses, electron degeneracy pressure fails completely. When Chandrasekhar presented this result to the scientific community, it was met with resistance. Arthur Eddington, one of the most prominent astrophysicists of the era, publicly ridiculed the idea. He could not accept the implication that a sufficiently massive star could collapse beyond the white dwarf stage. But Chandrasekhar was right. The mathematics was solid. The physics was correct. And in 1983, he was awarded the Nobel Prize in Physics for this work, more than 50 years after he first performed the calculation. So what happens when a stellar core exceeds the Chandrasekhar limit? What happens when gravity overwhelms electron degeneracy pressure? This is where the destruction of atoms begins. The scenario plays out inside massive stars, those with total masses of roughly 8 or more times the mass of the Sun. These stars live fast and die young. A star 20 times the mass of the Sun might burn through its nuclear fuel in only about 10 million years, compared to the roughly 10 billion year lifespan of a star like our Sun. These massive stars burn through the same fusion chain we described earlier, each stage building a new shell of heavier elements beneath the last. The process climbs the periodic table, element by element, until it reaches the end of the line, iron. And at the very center of the star, that iron core grows. As we discussed, iron is the end of the line for nuclear fusion. Fusing iron does not release energy, it absorbs energy. So when the core becomes predominantly iron, fusion stops. The energy source that has been holding the star up against gravity for millions of years simply shuts off. And in that moment, gravity takes over completely. The iron core has been growing, accumulating mass as silicon fusion continues to deposit iron onto it, like ash from a fire. When the core reaches approximately the Chandrasekhar limit, around 1.4 solar masses, electron degeneracy pressure can no longer support it. The core begins to collapse, and this collapse is fast, catastrophically fast. The core falls inward at speeds approaching a quarter of the speed of light. In less than a second, a core that was roughly the size of Earth, about 12,000 kilometers across, collapses to a ball roughly 20 to 30 kilometers in diameter. The density skyrockets. In a fraction of a second, matter that was already incredibly dense by any normal standard is compressed to densities of hundreds of trillions of times the density of water. At these densities, something remarkable and violent happens to the matter itself. This is the moment atoms die. As the core collapses, the electrons are compressed into an ever smaller volume. Remember, electron degeneracy pressure has already failed. The electrons are being pushed closer and closer to the nuclei, and at a critical density, a threshold is crossed. The electrons have so much energy from the compression that they can no longer remain as separate particles orbiting outside the nucleus. They are forced directly into the protons. This process has a name. It is called electron capture, sometimes referred to as inverse beta decay. And understanding it requires a brief detour into one of the 4 fundamental forces of nature, the weak nuclear force. You are probably familiar with the strong nuclear force, which holds atomic nuclei together, and the electromagnetic force, which governs how charged particles interact. The weak nuclear force is less well known, but equally fundamental. It is the force responsible for certain types of radioactive decay, and it governs interactions that can change one type of particle into another. Specifically, the weak force can transform a proton into a neutron, or a neutron into a proton, by exchanging particles called W and Z bosons. In ordinary radioactive beta decay, which happens naturally in certain unstable isotopes, a neutron inside a nucleus spontaneously transforms into a proton. When this happens, an electron is emitted from the nucleus, along with a tiny, nearly massless particle called an antineutrino. This is a well-understood process. It happens trillions of times every second in the rocks and soil beneath your feet. Potassium-40, a naturally radioactive isotope found in bananas, in your bones, and in granite, decays this way constantly. Electron capture is essentially the reverse of this process. Instead of a neutron becoming a proton and emitting an electron, a proton absorbs an electron and becomes a neutron. A neutrino is released in the process. Under normal conditions, this only happens in certain unstable atoms, where the nucleus has too many protons relative to neutrons. The atom captures one of its own inner electrons, converting a proton to a neutron and moving toward a more stable configuration. It is a gentle, natural process that happens at a modest rate in specific isotopes. But inside a collapsing stellar core, electron capture becomes something entirely different. It is no longer a gentle, occasional event. It becomes a catastrophic, wholesale transformation of matter. The gravitational compression forces electrons into protons whether they want to combine or not. The energies involved are so enormous that the process becomes unavoidable. Here is what is happening at the particle level. A proton sitting in an iron nucleus is a stable particle. Under normal circumstances, it would happily remain a proton forever. It has no reason to change. But when an electron is forced into contact with it at extreme energy, the weak nuclear force mediates a reaction. The proton and the electron merge. The proton's positive charge and the electron's negative charge cancel each other out. The result is an electrically neutral particle, a neutron, and a neutrino is released, carrying away energy and momentum. The neutrino, being an extraordinarily weakly interacting particle, flies straight out of the collapsing core and escapes into space. It barely interacts with anything. It passes through matter like light passes through glass. This reaction, electron plus proton, yields neutron plus neutrino, is happening to billions upon billions of protons simultaneously throughout the collapsing core. The scale is almost impossible to comprehend. In a fraction of a second, an enormous number of protons in the core are converted into neutrons. The electrons that defined atomic structure, that gave elements their chemical identities, that occupied quantum states according to the Pauli exclusion principle, are consumed. They do not just leave the atom, they cease to exist as electrons. They become part of neutrons. And this is the critical point that separates what happens inside a neutron star from any other extreme environment in the universe. Inside the core of a normal star, atoms are battered and ionized. Their electrons are stripped away by the heat. But the electrons still exist as free particles in the plasma, and the nuclei still exist as distinct objects with defined numbers of protons. If you cooled the plasma down, the electrons would recombine with the nuclei, and you would get atoms back. The elements are preserved even in the hottest stellar interiors. Inside a collapsing stellar core that is forming a neutron star, the electrons are not just stripped away, they are destroyed. They are absorbed into protons, converting those protons into neutrons. The protons themselves are destroyed as protons. They become neutrons. The element iron, which is defined by having 26 protons in its nucleus, ceases to be iron because many of those protons are no longer protons. They have been turned into neutrons. This is not crushing in the normal sense of the word. When you crush a can, you deform it, but the aluminum atoms remain aluminum. When you compress gas, the molecules get closer together, but they remain molecules. When gravity destroys atoms inside a collapsing stellar core, the fundamental particles change their identity. Protons become neutrons. Electrons cease to exist as separate particles. Elements lose their meaning. The periodic table, that catalogue of everything matter can be, becomes irrelevant. There is no iron. There is no silicon. There is no oxygen. There is no carbon. There are just neutrons. Let me explain why this does not happen under normal conditions, because understanding the energy threshold is important. Electron capture requires energy. The neutron is slightly heavier than the proton by about 0.14%. So to convert a proton into a neutron, you need to supply the mass difference as energy, according to Einstein's famous equation E equals mc squared. Under normal conditions, electrons in atoms simply do not have enough energy to trigger this conversion. They are bound to the atom at energy levels far below the threshold needed to turn protons into neutrons. The reaction is energetically forbidden. It is as if there is a wall that the electron cannot climb over. But gravitational compression changes the energy landscape completely. As the core collapses and electrons are squeezed into smaller and smaller volumes, the Pauli exclusion principle forces them into higher and higher energy states. Their energies increase dramatically, not because anyone is heating them, but because quantum mechanics demands it. At a critical density, the electrons reach energies high enough to overcome the mass difference between protons and neutrons. The wall that previously prevented the reaction is no longer tall enough. The electrons have been boosted to energies where electron capture becomes not just possible, but inevitable. And once the process begins, it accelerates. Each electron capture removes an electron from the pool, which means the remaining electrons must occupy even higher energy states, which means they have even more energy, which means electron capture happens even faster. It is a runaway process, a cascading collapse where the conversion of protons to neutrons feeds on itself and accelerates. The neutrinos released during this process carry away enormous amounts of energy. During the core collapse of a massive star, roughly 99% of the total gravitational energy released, an almost incomprehensible amount of energy, is carried away by neutrinos. The total energy radiated as neutrinos during a core collapse supernova is roughly 3 times 10 to the 46 joules. That is more energy than the Sun will emit over its entire 10 billion year lifetime. And virtually all of it comes out in a burst, lasting only about 10 seconds. We actually detected these neutrinos once. On February 23, 1987, a supernova designated SN 1987A was observed in the Large Magellanic Cloud, the small satellite galaxy about 168,000 light-years from Earth. Several hours before the light from the explosion reached Earth, neutrino detectors in Japan and the United States registered a brief pulse of neutrinos. Only 24 neutrinos were detected in total across all detectors, which might not sound like much. But remember, neutrinos barely interact with matter. Trillions upon trillions of neutrinos passed through the Earth during that event. The fact that we detected even 24 was remarkable and confirmed the basic physics of core collapse. The neutrinos arrived before the light because they were produced in the core itself during the collapse, while the light was produced later, when the shock wave from the collapse reached the star's surface. Those 24 particles were direct evidence of atoms being destroyed inside a collapsing stellar core. Each one was a messenger, a product of a proton and an electron merging into a neutron 168,000 years earlier. But the collapse of the core is only half the story. The core collapse also triggers one of the most violent explosions in the universe, the supernova itself. And understanding how the neutron star survives while the rest of the star is blown apart is crucial to the full picture. Here is what happens. As the inner core collapses, it reaches nuclear density in less than a second. At that point, the strong nuclear force between neutrons and the neutron degeneracy pressure we will discuss shortly bring the inner core to a sudden halt. The innermost material stops collapsing abruptly, but the outer layers of the core are still falling inward. They are plummeting toward the center at a significant fraction of the speed of light. And when this infalling material slams into the now rigid inner core, it bounces. The collision produces a massive shock wave that begins traveling outward through the still infalling material. Think of it like dropping a rubber ball onto a concrete floor. The ball hits the rigid surface and bounces. The collapsing outer core hits the rigid inner core and bounces. But this bounce involves matter traveling at tens of thousands of kilometers per second. The energies involved are beyond anything in everyday experience. The initial shockwave, however, does not have enough energy on its own to blow the star apart. As it pushes outward through the infalling material, it loses energy. It has to work against the relentless inward pressure of the outer layers, still falling toward the center. The shock stalls. It runs out of momentum and hangs there, a wall of compressed matter suspended between the outward push of the bounce and the inward pull of the still collapsing outer layers. This is where the neutrinos become critical again. The newly formed neutron core is radiating neutrinos at an almost inconceivable rate. And while neutrinos barely interact with matter under normal conditions, the densities just behind the stalled shockwave are so extreme that even neutrinos begin depositing some of their energy into the material. Only a small fraction of the total neutrino energy is absorbed, perhaps 5 to 10%. But the total neutrino energy is so enormous that even this small fraction is sufficient to revive the shockwave. The absorbed neutrino energy reheats the material behind the shock, pushing it outward again. The shockwave revives and begins ploughing through the outer layers of the star with renewed force. Within hours, the shockwave reaches the surface of the star, and when it does, the outer layers are blasted into space at thousands of kilometers per second. This is the supernova explosion, one of the most energetic events in the universe. For a few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of stars. The ejected material, enriched with heavy elements forged during the star's life and in the explosion itself, spreads into space, eventually mixing with interstellar gas clouds and contributing to the formation of new stars and planets. But at the center of this explosion, untouched by the outward blast, the neutron star remains. The inner core that halted the collapse, that caused the bounce, that radiated the neutrinos powering the explosion, that core survives. The star has been destroyed, but its heart, transformed beyond recognition into something no longer made of atoms, endures. The transition from ordinary atomic matter to neutron-rich degenerate matter is catastrophically sudden. The entire core collapse takes less than a second. In that brief moment, a volume of matter containing roughly 1.4 solar masses, matter that has existed as atoms for billions of years, matter that was forged in nuclear fusion reactions throughout the star's life, is converted into something completely different. The protons are consumed. The electrons are consumed. What remains is a dense ball of predominantly neutrons, packed together at densities that approach and exceed the density of an atomic nucleus itself. To put those densities into perspective, the nucleus of an atom, as we discussed, is already extraordinarily dense. All the mass of the atom is packed into a nucleus that is about 100,000 times smaller than the atom itself. Nuclear density is roughly 230 million metric tons per cubic centimeter. That means a single sugar cube of nuclear matter would weigh about 230 million tons. The matter inside a neutron star approaches, and in some regions, may exceed this density. A teaspoon of neutron star material would weigh somewhere around 4 billion tons on Earth. Not 4 billion kilograms, 4 billion tons. At these densities, the matter has no resemblance to anything in normal experience. The matter is a sea of neutrons, packed so tightly together that they are essentially touching, nucleus to nucleus, with no empty space whatsoever. The matter that was once mostly empty space, that was once clouds of electrons surrounding tiny nuclei separated by vast relative distances, has been compressed until all that empty space is gone. Think about what this means for the material's identity. Before the collapse, you had iron nuclei in the core of a star. Each iron nucleus contained 26 protons and 30 neutrons, held together by the strong nuclear force. These nuclei were surrounded by clouds of electrons, some bound and some free in the hot plasma. The matter had a chemical identity. It was iron. After the collapse, many of the 26 protons in each iron nucleus have been converted to neutrons through electron capture. The The nucleus no longer has 26 protons. It no longer has any defined place on the periodic table. The electrons that would have surrounded it are gone, consumed in the conversion process. What remains is a collection of neutrons, far more neutrons than the original nucleus contained, with a few surviving protons mixed in. The matter has lost its chemical identity completely. It is no longer any element. It is something else entirely. This transformation is irreversible under the conditions inside the neutron star. The neutrons cannot spontaneously convert back into protons and electrons because the density is too high. Under normal conditions, a free neutron is actually unstable. If you isolate a single neutron outside of a nucleus, it will decay in about 10 minutes, emitting an electron and an antineutrino and becoming a proton. This is ordinary beta decay, but inside a neutron star, this decay is blocked. The reason is, once again, the Pauli exclusion principle. If a neutron tried to decay into a proton and an electron, the electron would need to find an available quantum state to occupy. But at the extreme densities inside a neutron star, all the low-energy electron states are already filled. There is simply no room for another electron. The decay is forbidden because the final state is already occupied. The neutrons are trapped as neutrons, prevented from decaying by the very same quantum mechanical principle that once prevented electrons from collapsing into the nucleus. This is one of the most elegant and unsettling aspects of neutron star physics. The same rule, the Pauli exclusion principle, plays opposite roles at different stages. In a normal atom, it prevents electrons from collapsing and gives atoms their structure. In a white dwarf, it provides electron degeneracy pressure that resists gravitational collapse. But when gravity overwhelms that pressure and electron capture begins, the same principle then traps the resulting neutrons, preventing them from decaying back into the particles they came from. Quantum mechanics does not pick sides. It enforces its rules regardless of the consequences. The matter that emerges from this transformation is called neutron degenerate matter, and it is governed by entirely different physics than the atomic matter that preceded it. The electromagnetic force, which was the architect of atoms, is no longer the dominant structural force. In atomic matter, the electromagnetic force determined everything. It set the size of atoms, the arrangement of electrons, the nature of chemical bonds, the properties of materials. In neutron degenerate matter, the electromagnetic force is largely irrelevant. Neutrons carry no electrical charge. They do not interact electromagnetically with each other in the way that protons and electrons do. The forces that govern neutron degenerate matter are the strong nuclear force and, critically, neutron degeneracy pressure, another manifestation of the Pauli exclusion principle, this time applied to neutrons instead of electrons. We have crossed a threshold. The familiar world of atoms, elements, and chemistry is behind us. What lies ahead is a realm of matter governed by nuclear physics rather than atomic physics, by quantum degeneracy rather than electromagnetic structure, by forces that operate at scales 100,000 times smaller than the atom. The rules have changed completely, and the object that is formed from this alien matter, the neutron star, is one of the most extreme and least understood objects in the entire universe. The collapse of a stellar core, the destruction of atoms, the supernova bounce, and the formation of neutron degenerate matter all happen in an astonishingly compressed span of time. In those few violent seconds, billions of years of atomic existence are erased. Matter that has been atoms since it was forged in a previous generation of stars, matter that has cycled through interstellar clouds and stellar cores and planetary surfaces, matter that has maintained its chemical identity through every extreme environment the universe could throw at it, loses that identity forever. The protons become neutrons, the electrons vanish, the elements dissolve, And what remains is something the universe made precisely once before in its history, in the first moments after the Big Bang, when all matter was compressed to nuclear densities before expanding and cooling into the atoms that would eventually build everything we know. Inside a neutron star, the universe returns to that primordial state. Not everywhere, not across the entire cosmos, but in one small, incredibly dense object, roughly 20 kilometers across, matter is pushed back past the threshold of atomic existence and into a state that echoes the earliest moments of creation. Atoms cannot survive this journey. They were never meant to. They were built for a universe that had cooled and expanded enough to give them room to exist. Take away that room, compress the matter beyond what the electromagnetic force and electron degeneracy pressure can withstand, and atoms do not merely break, they transform into something else entirely. And the question that follows, perhaps the most important question of all, is what exactly is holding this new form of matter up? If electron degeneracy pressure has failed, if atoms have been destroyed, what prevents the neutron star from collapsing further? What stops the collapse from continuing all the way to a black hole? The answer lies in the same quantum principle that has been shaping this story from the beginning, but now applied to an entirely different particle. And the physics of what comes next is just as strange as the physics of what we have already seen. We have just watched atoms die. We have seen gravity overwhelm the electromagnetic force, compress electrons into protons, and convert ordinary atomic matter into a dense sea of neutrons. The periodic table has been erased. Chemistry has ceased to exist. The familiar architecture of matter, the architecture that builds everything you have ever known, has been completely dismantled. And yet the collapse stopped. This is perhaps the most remarkable part of the entire story. The gravitational force that just crushed atoms out of existence, the force that overwhelmed the electromagnetic interaction and broke through electron degeneracy pressure, the force that compressed a stellar core the size of Earth into a ball smaller than a city. That force was stopped. Something halted the collapse. Something pushed back against gravity at a density where atoms themselves could not survive. And understanding what that something is requires us to return to the same quantum mechanical principle that has been running through this entire story like a thread. The Pauli exclusion principle. But this time, it is not electrons obeying the rule, it is neutrons. The Pauli exclusion principle does not apply only to electrons. It applies to all particles in a category physicists call fermions. A fermion is any particle with a quantum property called half-integer spin. Electrons are fermions, protons are fermions, and critically, neutrons are fermions. They all obey the same rule. No two identical fermions can occupy the same quantum state at the same time. This is not a suggestion. It is not a tendency. It is an absolute law of quantum mechanics, as inviolable as the speed of light being the cosmic speed limit. There is no known exception to it anywhere in the universe. So when the collapsing stellar core converts most of its protons and electrons into neutrons, those neutrons inherit the same quantum restrictions that electrons had. As the neutrons are packed closer and closer together by gravity, they begin running out of available quantum states, just as the electrons did before them. The low energy states fill up first. As more neutrons are crammed into the same volume, they are forced into higher and higher energy states. This means they must move faster, and as they are forced to move faster, they exert an outward pressure. This pressure is called neutron degeneracy pressure. and it is the direct analogue of the electron degeneracy pressure that supports white dwarfs. The physics is identical in principle. The particles are different, electrons in one case and neutrons in the other, but the underlying quantum mechanics is the same. Fermions resist being squeezed into the same quantum states. That resistance manifests as pressure. And in the case of neutrons, that pressure is enormously stronger than electron degeneracy pressure, because neutrons are much more massive than electrons, roughly 1839 times more massive. This means that at the extreme densities inside a neutron star, neutron degeneracy pressure can resist gravitational forces that electron degeneracy pressure could not even come close to withstanding. There is another force contributing to the structural support at these densities as well, and it would be misleading to attribute everything solely to degeneracy pressure. The strong nuclear force, the same force that holds protons and neutrons together inside atomic nuclei, also plays a crucial role. At the densities inside a neutron star, neutrons are packed so closely together that they are essentially touching, separated by distances comparable to the range of the strong force. At very short ranges, the strong force between neutrons is repulsive. When neutrons are pushed too close together, the strong force pushes back. This nuclear repulsion adds to the outward pressure, supporting the star against further collapse. The balance between these outward pressures, neutron degeneracy pressure, and the repulsive component of the strong nuclear force, and the inward pull of gravity, is what defines a neutron star. It is an equilibrium, a standoff between quantum mechanics and gravity. Gravity wants to compress the matter further. Neutron degeneracy pressure and nuclear forces resist. The result is an object of extraordinary density and extraordinary stability, one that can persist for billions of years in this state without collapsing or expanding. Let me describe the properties of this object, because they are unlike anything else in the universe. A typical neutron star has a mass between about 1.4 and roughly 2 solar masses. All of that mass is compressed into a sphere approximately 20 kilometers in diameter. 20 kilometers. That is roughly the distance you might drive across a small city. The object, containing more mass than our entire Sun, fits within a space that would comfortably sit inside the boundaries of a medium-sized metropolitan area. The density of this material is staggering. The average density of a neutron star is roughly 400 trillion grams per cubic centimeter, approximately 2 to 3 times the density of an atomic nucleus. To put that differently, a neutron star packs more mass than the entire Sun into a volume smaller than most cities. If Earth were compressed to the same density, the entire planet would fit inside a sphere about 300 meters across, roughly the height of the Eiffel Tower laid on its side. Every atom of every mountain, every ocean, every continent, every living thing, all of it crushed into a space you could jog across in well under a minute. And if you could somehow extract even a tiny fragment of neutron star matter and bring it to Earth's surface, it would not just sit there. It would immediately begin to expand explosively, because the only thing keeping neutron star matter compressed is the intense gravity of the neutron star itself. Remove the gravity, and the matter has no reason to stay in that state. The degeneracy pressure and nuclear forces would blast it apart. The gravitational field at the surface of a neutron star is roughly 200 billion times the gravitational field at the surface of Earth. If you could somehow stand on the surface of a neutron star, which you absolutely could not, because you would be killed in dozens of different ways simultaneously, but if you could, you would weigh about 200 billion times your weight on Earth. A human being weighing 70 kilograms on Earth would weigh roughly 14 trillion kilograms on a neutron star's surface. The gravitational force is so extreme that it distorts the shape of the star itself. Neutron stars are among the most perfectly spherical objects in the universe. Any mountains or surface irregularities can only be millimeters or at most centimeters tall. Gravity flattens everything. A mountain 1 centimeter high on a neutron star would contain more gravitational potential energy than the largest earthquakes on Earth release. The surface gravity also produces measurable effects on light itself. Photons escaping from the surface of a neutron star lose energy climbing out of the gravitational well. This is called gravitational redshift. Light emitted from a neutron star's surface is redshifted by roughly 20 to 30% by the time it reaches a distant observer. The star's gravity is literally pulling on light, draining its energy, stretching its wavelength. If you could see a neutron star up close, the extreme gravity would also bend light around the star, allowing you to see more than half of its surface at once. Light from the far side of the star would curve around and reach your eyes. The star would appear larger than it actually is, and features on the backside of the star that should be hidden from view would be partially visible. General relativity, Einstein's theory of gravity as the curvature of space-time, becomes essential for understanding the behavior of light and matter near a neutron star. Newtonian gravity, which works perfectly well for everyday situations and even for most astronomical applications, fails near neutron stars. The gravitational field is strong enough that the curvature of space-time itself becomes significant. Time runs measurably slower at the surface of a neutron star compared to a point far away. A clock on the surface would tick about 20 to 30% slower than a clock in distant space. If you watched a neutron star from a safe distance, events on its surface would appear to happen in slow motion. Neutron stars also rotate, and many of them rotate extraordinarily fast. When the core of a massive star collapses to form a neutron star, the principle of conservation of angular momentum comes into play. This is the same principle that causes an ice skater to spin faster when pulling their arms in. The original stellar core was rotating slowly, perhaps once every few days or weeks. But when it collapsed from a diameter of thousands of kilometers to roughly 20 kilometers, that rotation sped up enormously. Some neutron stars rotate hundreds of times per second. The fastest known neutron stars, called millisecond pulsars, spin at rates exceeding 700 revolutions per second. A point on the equator of such a star is moving at a significant fraction of the speed of light. And yet, the star holds together. The gravity is so intense that even at these rotational speeds, the centrifugal force at the equator is not sufficient to tear the star apart. These rapidly rotating neutron stars often have incredibly strong magnetic fields. The magnetic field of a typical neutron star is roughly 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields 1,000 times stronger still, reaching quadrillions of times Earth's field strength. These magnetic fields are the strongest known in the universe. A magnetar's field is so powerful that at a distance of about 1,000 kilometers, it would erase every credit card on Earth, disrupt electronics, and be lethal to a human being. At closer ranges, the field would distort the shapes of atoms and fundamentally alter the laws of chemistry. The field is strong enough to affect the vacuum of space itself, causing it to become birefringent, meaning light passing through the magnetized vacuum would split into two polarized beams traveling at slightly different speeds. This effect, called vacuum birefringence, was predicted by quantum electrodynamics decades ago and has recently been observed in light from neutron stars. For decades, neutron stars were purely theoretical objects. Physicists like Walter Baudeur and Fritz Zwicky had proposed their existence as early as 1934, suggesting that neutron stars might form in supernova explosions. But no one had ever observed one. The objects were so small and so far away that detecting them seemed nearly impossible. A sphere 20 kilometers across, sitting hundreds or thousands of light years away, emitting most of its radiation in wavelengths invisible to the naked eye. How would you ever find such a thing? The answer came by accident. In 1967, a graduate student named Jocelyn Bell Burnell was working at the Mullard Radio Astronomy Observatory in Cambridge, England. She was using a newly built radio telescope to study a phenomenon called interplanetary scintillation, the twinkling of distant radio sources caused by the solar wind. While sifting through hundreds of feet of paper chart recordings, she noticed something strange. A regular, repeating signal pulsing with extraordinary precision, one pulse every 1.337 seconds. The signal was so regular, so perfectly timed, that for a brief period the team half-jokingly labelled it LGM-1, for Little Green Men 1. The precision seemed almost artificial, as if someone, or something, were deliberately broadcasting a signal. But Bell Burnell and her supervisor, Anthony Hugh Ish, soon found more of these pulsing sources in different parts of the sky. If these were alien signals, there would need to be multiple alien civilizations, all broadcasting with the same strange characteristics. The more natural explanation was that these were a previously unknown type of astronomical object. They were quickly identified as rapidly rotating neutron stars, their beams of radio emission sweeping across Earth like cosmic lighthouse beams. Each pulse corresponded to one rotation of the star. The discovery was monumental. It was the first observational proof that neutron stars actually exist. These objects, predicted on paper more than 30 years earlier, were suddenly real. You could point a telescope at the sky and detect their signals. The discovery earned a Nobel Prize in 1974, though controversially, it was awarded to Hugh Ish and not to Bell Burnell, the person who actually made the discovery. Regardless of that injustice, the detection of pulsars opened an entirely new window on the universe and gave physicists their first tool for studying matter under the most extreme conditions nature provides. But perhaps the strangest properties of neutron star matter have nothing to do with gravity, magnetism, or rotation. They have to do with quantum mechanics, operating at scales that should be impossible. In our everyday experience, quantum effects are confined to the atomic and subatomic world. You never notice quantum behavior in your daily life because the objects around you are made of trillions upon trillions of particles, and their individual quantum properties average out to produce the smooth, predictable, classical behavior you observe. A baseball does not tunnel through a wall. A car does not exist in a superposition of two locations simultaneously. Quantum mechanics governs the microscopic world, but the macroscopic world follows classical physics, or so it seems. Inside a neutron star, quantum mechanical effects operate at macroscopic scales. The entire interior of the star is a quantum system, and two of the most striking predictions about this quantum behavior involve phenomena that we normally associate only with laboratory physics at temperatures near absolute zero: superfluidity and superconductivity. Superfluidity is a state of matter in which a fluid flows with zero viscosity, absolutely zero. No friction, no resistance to flow, no energy loss. In normal fluids, viscosity causes resistance. Honey flows slowly because it has high viscosity. Water flows faster because it has lower viscosity. But even water has some viscosity. It resists flow, however slightly. A superfluid has none. If you set a superfluid in motion, it will continue flowing forever without losing any energy. It never slows down. It never stops. This sounds like science fiction, but superfluidity is a well-established phenomenon in laboratory physics. Helium-4, when cooled below about 2.2 degrees above absolute zero, becomes a superfluid. It was first observed experimentally by Piotr Kapitsa in 1938. In a neutron star, physicists believe the neutrons in the interior form a superfluid. This idea was first proposed by Arkady Migdal in 1959 and has been developed extensively since then. The mechanism is analogous to what happens in laboratory superfluids and superconductors, but adapted to the extreme conditions inside a neutron star. At the enormous densities in the star's interior, neutrons can form pairs, called Cooper pairs, through an attractive component of the nuclear force. These paired neutrons behave as a single quantum entity, a boson rather than a fermion, and bosons do not obey the Pauli exclusion principle. They can all occupy the same quantum state simultaneously. When enough neutrons pair up in this way, the resulting fluid transitions into a superfluid state. Evidence for neutron superfluidity comes from observations of pulsar glitches. Pulsars are extraordinarily precise clocks. Their rotation rates are measurable to extreme accuracy, and they slow down very gradually over time as they lose rotational energy through radiation. But occasionally, a pulsar will experience a sudden, tiny increase in its rotation rate, a glitch. The star abruptly speeds up by a tiny fraction and then gradually relaxes back toward its previous rate over days, weeks, or months. These glitches have been observed in many pulsars, and the leading explanation involves the superfluid interior. The idea is that the superfluid neutrons in the star's interior rotate by forming quantized vortices, tiny tornado-like tubes of circulation. In a superfluid, rotation does not happen smoothly. It happens through the formation of discrete vortex lines, each carrying a specific quantum of angular momentum. As the star's solid crust slows down due to electromagnetic braking, the superfluid interior does not slow down at the same rate, because superfluids have no viscosity, and therefore no mechanism to transfer angular momentum smoothly. A lag builds up between the slower crust and the faster superfluid interior. Eventually, the vortex lines in the superfluid suddenly unpin from the crust, transfer angular momentum to it, and the crust spins up abruptly. This is the glitch. The fact that glitches happen repeatedly and with characteristic relaxation timescales provides indirect but compelling evidence that the neutron star interior is indeed superfluid. The behavior matches what you would expect from a superfluid rotating through quantized vortices. It is quantum mechanics operating not at the scale of atoms, but at the scale of a star. A quantum phenomenon governing the rotation of an object 20 kilometers across, containing more mass than the Sun. That is extraordinary. Alongside the neutron superfluid, the small fraction of protons that survive inside the neutron star are predicted to form a superconductor. Superconductivity is the electrical analog of superfluidity. In a superconductor, electrical current flows with zero resistance. No energy is lost to heating. No voltage is needed to maintain the current. Once started, a superconducting current flows forever. Superconductivity was first discovered in 1911 in mercury cooled to near absolute zero. In the decades since, it has been observed in many materials at low temperatures. Inside a neutron star, the surviving protons, which make up roughly 5 to 10% of the particles in certain regions, can also form Cooper pairs through the nuclear force. These paired protons, being charged, create a superconducting fluid. The magnetic field of the neutron star threads through this superconductor in the form of quantized flux tubes, discrete lines of magnetic field, each carrying a single quantum of magnetic flux. The interaction between the neutron superfluid vortices and the proton superconductor flux tubes creates complex dynamics that are still being studied. These interactions may contribute to pulsar timing irregularities and to the evolution of the neutron star's magnetic field over time. Think about what this means. Inside a neutron star, you have a superfluid made of neutrons and a superconductor made of protons, coexisting in the same volume, threaded by the strongest magnetic fields in the universe, under gravitational conditions so extreme that space-time itself is measurably curved. These are quantum phenomena that in a laboratory require temperatures within fractions of a degree of absolute zero, happening inside an object where temperatures can reach billions of degrees in the moments after formation. The reason superfluidity and superconductivity can exist at such high temperatures inside a neutron star is that the relevant energy scale is set by the nuclear force, which is extraordinarily strong. the pairing energy for neutrons and protons at nuclear densities is so high that it corresponds to temperatures of billions of degrees. What counts as cold for nuclear matter is unimaginably hot by everyday standards. It is worth pausing to contrast all of this with what happens in a white dwarf, the less extreme cousin of the neutron star. A white dwarf is supported by electron degeneracy pressure. Its matter is compressed, but still made of atoms, or more precisely, nuclei and free electrons. The densities are around 1 million times the density of water, about 1 million grams per cubic centimetre, dense enough that a marble-sized piece would weigh about as much as a small car. That is impressive, but it is still roughly several 100 million times less dense than a neutron star. In a white dwarf, the nuclei retain their identity. Iron remains iron, carbon remains carbon. The periodic table still applies. Chemistry is distorted but not abolished. The electrons still exist and still provide structural support. In a neutron star, the matter has gone one entire step further. The electrons are gone. The protons are mostly converted to neutrons. The structural support has shifted from electron degeneracy to neutron degeneracy and nuclear forces. The matter is no longer atomic, it is nuclear. A white dwarf is matter squeezed to its atomic limit. A neutron star is matter squeezed beyond that limit, into a state where atoms cannot exist. Now here is the critical question. Is neutron degeneracy pressure, combined with the repulsive, strong nuclear force, strong enough to resist gravity indefinitely? Or does it too have a limit, just as electron degeneracy pressure had the Chandrasekhar limit? The answer is yes. Neutron degeneracy pressure has a limit. There is a maximum mass that a neutron star can have before even neutron degeneracy pressure and nuclear forces are overwhelmed by gravity. This maximum mass is called the Tolman-Oppenheimer-Volkoff limit, or the TOV limit, named after Richard Tolman, J. Robert Oppenheimer, and George Volkoff, who calculated it in 1939. The physics behind the TOV limit is similar in spirit to the physics behind the Chandrasekhar limit, but involves general relativity in a fundamental way. At the extreme densities inside a neutron star, Newtonian gravity is no longer adequate. You must use Einstein's general theory of relativity, which describes gravity as the curvature of spacetime caused by mass and energy. And general relativity introduces a crucial complication. In Newtonian gravity, pressure helps support a star against collapse. Pressure pushes outward, gravity pulls inward. But in general relativity, pressure itself is a source of gravity. Pressure contributes to the curvature of spacetime. This means that at extremely high densities, the very pressure that is supposed to resist collapse actually makes gravity stronger. It is a self-defeating mechanism. The harder the matter pushes back against gravity, the stronger gravity becomes. There is a point where this feedback loop runs away, where adding more pressure only makes the gravitational pull increase faster than the support increases. Beyond that point, nothing can stop the collapse. The exact value of the TOV limit is not known with precision, and this is one of the most important open questions in astrophysics. The reason for the uncertainty is that the TOV limit depends on something called the equation of state of ultra-dense matter. The equation of state describes how pressure relates to density for a given type of matter. For ordinary matter, we know the equation of state very well. We can predict how gas, liquid, or solid matter behaves under various pressures and temperatures. But for matter at neutron star densities, particularly in the deep interior where densities may exceed normal nuclear density by factors of several, the equation of state is not well known. We cannot recreate these conditions in any laboratory on Earth. Our particle accelerators can briefly create tiny volumes of matter at comparable densities in heavy ion collisions, but these exist for only fractions of a second and involve conditions that are not identical to those inside a neutron star. Different models of the equation of state give different values for the TOV limit. Current estimates place it somewhere between about 2 and 2.4 solar masses, with most theoretical models and observational constraints pointing toward a value around 2.2 to 2.3 solar masses. The most massive neutron stars that have been reliably measured have masses close to 2 solar masses, which rules out some of the softer equations of state that would predict a lower maximum mass. If a neutron star's mass exceeds the TOV limit, there is no known force in nature that can stop the collapse. Neutron degeneracy pressure fails. The repulsive strong force is overwhelmed. The matter collapses to a black hole, an object where gravity has won completely and permanently, where space-time is curved so severely that not even light can escape. The black hole represents the ultimate victory of gravity over all forms of matter and energy. Nothing pushes back, nothing resists. The collapse proceeds to a singularity, a point of theoretically infinite density, where our current understanding of physics breaks down entirely. This means neutron stars exist in an extraordinarily narrow range of conditions. They must have masses above the Chandrasekhar limit of about 1.4 solar masses, because below that mass, electron degeneracy pressure can support the object, and it remains a white dwarf. And they must have masses below the TOV limit of roughly 2 to 2.4 solar masses, because above that mass, even neutron degeneracy pressure and nuclear forces cannot resist gravity, and the object collapses to a black hole. The window is narrow. Neutron stars occupy a band of only about 1 solar mass in width between white dwarfs and black holes. They exist on a knife edge, a narrow ledge between two very different fates. This narrow range is not just a theoretical curiosity. It has real physical consequences for how neutron stars form and what they can become. A stellar core that collapses and produces a remnant within this mass window becomes a neutron star. A remnant slightly less massive becomes a white dwarf. A remnant slightly more massive becomes a black hole. The boundaries are sharp and unforgiving. Nature does not produce objects that hover between these categories. The physics forces the remnant into one state or another. And here is something remarkable about this picture. Everything we have discussed, the electron degeneracy that supports white dwarfs, the neutron degeneracy that supports neutron stars, the gravitational collapse that can overwhelm both, all of it comes down to the interaction between just two things: gravity and the Pauli exclusion principle. Gravity pulls matter together. The Pauli exclusion principle pushes back by forbidding fermions from sharing quantum states. In a white dwarf, the Pauli exclusion principle applied to electrons provides enough resistance to hold the star up, as long as the mass is below the Chandrasekhar limit. Cross that limit, and electrons lose. In a neutron star, the same principle applied to neutrons provides enough resistance to hold the star up, as long as the mass is below the TOV limit. Cross that limit, and neutrons lose too. Gravity is the only force that gets stronger without limit as you add more mass. Every other force either saturates, cancels out, or becomes insufficient at extreme scales. Gravity just keeps growing, and at each threshold, another form of quantum mechanical resistance falls. The matter inside a neutron star is governed by rules that have no analogue in everyday experience. It is matter where chemistry does not exist, where the periodic table is meaningless, where the structural support comes not from electromagnetic interactions between atoms, but from quantum mechanical restrictions on neutrons and from nuclear forces operating at scales smaller than an atomic nucleus. It is matter where quantum phenomena like superfluidity and superconductivity Effects that, in the laboratory, require temperatures near absolute zero, emerge at temperatures of billions of degrees because the relevant energy scales are set by the nuclear force rather than by the electromagnetic force. It is matter so dense that it outweighs entire mountains in a single thimbleful, so compact that an object with more mass than the Sun fits in a space smaller than a city, and so gravitationally extreme that it warps space-time, bends light, and slows time. This is what replaced the atoms. When gravity crushed ordinary matter beyond the breaking point, when the electromagnetic force lost its grip and electron degeneracy pressure failed, when protons absorbed electrons and became neutrons in the cascading fury of core collapse, this is what emerged on the other side. Not nothing, not a void. A new form of matter, governed by new rules, stabilized by a new kind of pressure, existing under conditions so extreme that they push our understanding of physics to its absolute limits. But even this extraordinary picture is incomplete, because a neutron star is not simply a uniform ball of neutrons. It has structure, it has layers, and as you descend from the surface into the deep interior, the matter changes in ways that become progressively stranger and progressively less understood. The outer layers of a neutron star still contain recognizable nuclei. The inner layers contain matter in states that might not exist anywhere else in the observable universe. And at the very center, in the innermost core, where densities exceed anything we can replicate or calculate with confidence, the matter may take forms so exotic that we do not yet have the physics to describe them. The new rules of matter that govern a neutron star are extraordinary enough. But the mysteries that remain, the questions about what lies in the deepest interior, those are where the truly unknown begins. If you have been imagining a neutron star as a uniform ball of neutrons, a single, featureless mass of identical particles packed together from surface to center, you would be wrong, and you would not be alone. That simplified picture is often how neutron stars are described in popular science. But the reality is far more complex and far more fascinating. A neutron star has layers. It has structure, and as you descend from the surface into the interior, the matter changes in ways that become progressively more extreme and progressively less understood, passing through states of matter that may not exist anywhere else in the observable universe. Think of it like descending into the earth. On the surface, you have solid rock and soil. Go deeper and you reach denser rock. Deeper still and you hit the molten outer core. At the very center is the solid inner core, mostly iron and nickel, compressed by the weight of everything above it. Each layer has different properties, different composition, different behavior. A neutron star is similar in concept, but wildly different in the physics. Each layer represents a different regime of matter, governed by different rules. And the deeper you go, the more alien those rules become. Let us start at the surface and work our way down. The outermost layer of a neutron star is called the outer crust, and it is the last place where anything resembling ordinary atoms can exist. The outer crust is thin, perhaps only a few hundred meters to a kilometer deep, but it is physically remarkable. The matter here is arranged in a crystalline lattice, a regular geometric grid of atomic nuclei, primarily iron and other elements near iron on the periodic table. These nuclei are completely ionized, meaning all their electrons have been stripped away by the extreme conditions. But the electrons have not been consumed through electron capture, not yet. At these relatively low densities, at least low by neutron star standards, the electrons still exist as free particles. They form a sea, a gas of electrons that permeates the spaces between the nuclei, flowing freely through the lattice like water through a sponge. This arrangement is actually somewhat familiar. It resembles the structure of a metal, where positively charged ions sit in a lattice surrounded by a sea of free electrons. The densities are enormously higher, but the broad picture is recognizable. If you could somehow extract a tiny sample of the outer crust and examine it, you would find organized, structured matter, not the chaotic sea of neutrons that exists deeper in the star. The nuclei here still have protons. They still have defined atomic numbers. They are still, in some sense, elements. But the crystalline structure of the outer crust is extraordinary in its own right. The lattice is held together by incredibly strong forces. Estimates suggest this lattice has a strength roughly 10 billion times greater than that of steel. Neutron star crust material is the strongest known material in the universe. It can withstand stresses that would shatter any substance found on Earth. This immense strength is why neutron star mountains, if they exist at all, are at most a few centimeters tall. The crust is strong, but the gravitational force trying to flatten it is so overwhelming that even the strongest known material can only sustain the tiniest irregularities. As you descend through the outer crust, the density increases. And as the density increases, the balance between protons and neutrons inside the nuclei shifts. Under normal conditions, stable nuclei have roughly equal numbers of protons and neutrons, or slightly more neutrons than protons in heavier elements. Iron, for example, has 26 protons and 30 neutrons in its most common isotope. But as pressure increases deeper in the crust, it becomes energetically favorable for nuclei to have more neutrons. Electron capture begins to occur at the edges. Electrons are pushed into protons, converting them to neutrons, creating nuclei that are far more neutron-rich than anything that exists naturally on Earth. These are exotic isotopes, nuclei with the same number of protons as familiar elements, but with far more neutrons than any stable version of that element. At a depth of roughly 1 kilometer or so below the surface, something remarkable happens. The nuclei become so neutron-rich that they can no longer hold all their neutrons. The neutrons begin to leak out. This boundary is called the neutron drip line, and it marks the transition from the outer crust to the inner crust. Below this point, free neutrons exist outside the nuclei, floating in the spaces between them. The matter is now a mixture of 3 components: neutron-rich nuclei that are still recognizable as discrete objects, a sea of free electrons, and a gas of free neutrons that have dripped out of the overstuffed nuclei. This is unlike anything found anywhere else in the natural universe under stable conditions. As we discussed earlier, a free neutron outside a nucleus is unstable and will quickly decay back into a proton and an electron. But inside a neutron star, the density is so extreme that there are no available quantum states for those decay products to occupy. The Pauli exclusion principle blocks the decay. The free neutrons are trapped, stabilized by the very density that liberated them from the nuclei in the first place. The inner crust gets stranger still. As you go deeper and the density continues to climb, the nuclei begin to deform. Under the crushing pressure, they are no longer spherical. They stretch and flatten into shapes that physicists have named after Italian foods, and this terminology has stuck so firmly in the scientific literature that it is now the standard way to describe these structures. Collectively, they are called nuclear pasta. At certain densities, the nuclei elongate into rod-like shapes. These are called spaghetti. Go deeper, and the rods merge into flat sheets. These are called lasagna. Deeper still, the sheets develop cylindrical holes running through them. These are called anti-spaghetti, or bucatini. And at the very bottom of the inner crust, just before the transition to the liquid core, the matter forms a Swiss cheese-like structure of spherical voids inside a continuous nuclear medium. These are sometimes called gnocchi, though the naming convention becomes less standardized at this point. Nuclear pasta may sound whimsical, but it is taken very seriously by physicists. The shapes arise from the competition between the strong nuclear force, which tries to pull nuclear matter together, and the electromagnetic force, which tries to push the protons apart. At different densities, different geometries minimize the total energy of the system. The result is these exotic structures, neither fully solid nor fully liquid, neither discrete nuclei nor uniform nuclear matter. They exist at the boundary between two states, and they may constitute some of the strongest material in the universe. Simulations suggest nuclear pasta phases could be even stronger than the crystalline lattice of the outer crust. Some calculations indicate that nuclear pasta occupies only a thin layer, perhaps 100 meters deep. But this thin layer might contain a significant fraction of the crust's total mass, because the density increases so rapidly with depth. Below the inner crust, you enter the outer core of the neutron star, and here, nuclei no longer exist in any form. The matter has fully transitioned into a continuous fluid. There are no more discrete nuclei, no more crystalline lattices, no more pasta shapes. The outer core is a dense liquid composed primarily of neutrons, with a small admixture of protons and electrons, roughly 5 to 10% each. This is the neutron degenerate matter we discussed at length. The neutrons are packed so closely together that they are essentially in contact, interacting through the strong nuclear force and resisting further compression through neutron degeneracy pressure. The protons and electrons are present because the system requires a certain balance to minimize its total energy. Beta equilibrium, the balance between electron capture and neutron decay, determines the exact proportions. The outer core is where the neutron superfluid and the proton superconductor we discussed earlier are believed to exist. The neutrons pair up through the attractive component of the nuclear force at certain densities and form a superfluid. The protons similarly pair up and form a superconductor. These quantum phenomena coexist in this dense nuclear fluid, producing the macroscopic quantum effects that we observe indirectly through pulsar glitches and magnetic field behavior. The outer core occupies most of the neutron star's volume. By radius, it extends from roughly a kilometer or two below the surface down to several kilometers from the center. It is the dominant component of the star, the region where most of the mass resides, and the region whose properties most strongly determine the star's overall behavior. And while the physics of the outer core is extreme, it is at least within the reach of nuclear physics models. We can extrapolate from what we know about nuclear forces, about neutron-neutron and neutron-proton interactions, and about the properties of nuclear matter at densities close to normal nuclear density. The extrapolation is uncertain, but it is grounded in physics we have tested in laboratories and particle accelerators. But at the very center of the neutron star lies something else entirely: the inner core. And this is where our understanding begins to genuinely break down. The inner core of a neutron star is the most mysterious region of dense matter in the known universe. Here, the density may reach 5 to 10 times normal nuclear density, possibly more. These are densities that have never been achieved in any sustained way in any laboratory on Earth. Heavy ion colliders like the ones at Brookhaven National Laboratory and at CERN can briefly create tiny volumes of matter at comparable densities by smashing heavy nuclei together at nearly the speed of light. But these collisions last for only a trillionth of a second. The matter explodes outward almost instantly. There is no way to study it in a stable, sustained state. Inside a neutron star, this density is maintained permanently, held in place by gravity, existing in a state of equilibrium that has persisted for millions or billions of years. The central question is straightforward: what is the matter made of? At normal nuclear density, matter consists of neutrons and protons, which are themselves made of quarks held together by gluons. But at the extreme densities of the inner core, several possibilities emerge, and none of them has been confirmed or ruled out. One possibility is that the neutrons and protons in the inner core dissolve. At sufficiently high densities, the quarks inside neutrons and protons might no longer be confined within individual particles. Instead, they could move freely throughout the entire core, forming a state called quark matter, or a quark-gluon plasma. Under normal conditions, quarks are permanently confined inside protons and neutrons by the strong force. You cannot isolate a single quark. If you try to pull two quarks apart, the energy in the strong force field between them becomes so great that it creates new quarks from the vacuum, and these new quarks bind with the originals to form new particles. Quarks are always found in groups, never alone. But at extreme densities, when neutrons are packed so tightly that the quarks inside neighboring neutrons are closer to each other than the quarks within the same neutron, the boundaries between individual neutrons may dissolve. Quarks would no longer belong to specific neutrons. They would roam freely through a shared space. The neutrons themselves would cease to exist as distinct objects, melting into a continuous sea of quarks and gluons. If this happens, the inner core of a neutron star would contain matter in a state that has not existed freely in the universe since the first microseconds after the Big Bang, when the entire cosmos was a quark-gluon plasma before it cooled enough for quarks to condense into protons and neutrons. Another possibility involves particles called hyperons. Hyperons are baryons, particles in the same family as protons and neutrons, but they contain one or more strange quarks in addition to the up and down quarks found in ordinary matter. Under normal conditions, hyperons are unstable. They decay in fractions of a second, but at the extreme densities inside the inner core, it may become energetically favorable for some neutrons to convert into hyperons. The reasoning is that the Pauli exclusion principle makes it increasingly costly in energy terms to add more neutrons to an already neutron-dense environment. At some point, it becomes cheaper, energy-wise, to create a different type of particle, a hyperon, rather than squeeze another neutron into an already overcrowded quantum state. If hyperons appear in significant numbers, they change the equation of state of the matter, generally making it softer, meaning less resistant to compression. This creates a puzzle known as the hyperon puzzle. If hyperons soften the equation of state, the maximum mass a neutron star can support should decrease. But we have observed neutron stars with masses close to 2 solar masses, which some hyperon models struggle to explain. Resolving this tension is an active area of research. Yet another exotic possibility is color superconductivity. In ordinary superconductivity, electrons form Cooper pairs that carry electrical current without resistance. In color superconductivity, quarks form pairs bound together by the strong force. The word color here does not refer to visible color. It refers to the quantum property called color charge that quarks carry, analogous to electrical charge, but for the strong force. If the quarks in the inner core are deconfined and form a quark matter phase, they might pair up in specific ways that create a color superconducting state. Multiple types of color superconductivity have been proposed by theorists, with names like the color flavor-locked phase, and each would have different physical properties. Some of these phases might be more resistant to gravitational compression than others, affecting the maximum mass a neutron star can sustain. Here is what is crucial to understand about all of these possibilities. None of them has been confirmed. None of them has been ruled out. The inner core of a neutron star remains one of the great unsolved problems in physics. We do not know whether the core contains pure neutron matter, quark matter, hyperonic matter, color superconducting matter, or some combination. We do not even know if there is a sharp boundary between phases or a gradual transition. These are open questions, the subjects of hundreds of research papers published every year by physicists around the world. The inner core is a frontier, perhaps the last great frontier of matter itself, where the laws of physics are pushed to their absolute limits and where the answers remain genuinely unknown. So how do physicists study something they cannot see, cannot touch, and cannot recreate in a laboratory? The answer is that they study it indirectly, using observations of neutron stars from across the electromagnetic spectrum and increasingly through gravitational waves. Pulsars provide one of the most powerful tools. Because pulsars are such precise clocks, tiny variations in their rotation rates carry information about their internal structure. The glitches we discussed earlier, those sudden speed-ups caused by the interaction between the superfluid interior and the solid crust, tell us about the fraction of the star that is superfluid and how the superfluid couples to the crust. The rate at which pulsars slow down over time tells us about their magnetic fields and how those fields evolve. The precise timing of pulsar signals, measured over years and decades, allows physicists to measure neutron star masses with extraordinary accuracy. These mass measurements are critical because they constrain the equation of state. If we observe a neutron star with a mass of 2 solar masses, any equation of state that predicts a maximum mass lower than that is immediately ruled out. The discovery of massive neutron stars in the 2010s, with masses approaching and possibly exceeding 2 solar masses, eliminated many theoretical models and significantly narrowed the range of possibilities. X-ray observations provide another window. Several space-based telescopes, including a NASA instrument called NICER, mounted on the International Space Station, have been measuring X-rays emitted from the surfaces of neutron stars. By carefully analyzing how the X-ray brightness varies as the star rotates, and by accounting for the effects of general relativity on the light traveling from the star's surface to our detectors, physicists can estimate both the mass and the radius of the neutron star simultaneously. This is enormously valuable because the relationship between mass and radius is determined by the equation of state. Different equations of state predict different mass-radius relationships. By measuring several neutron stars and plotting their masses against their radii, physicists can identify which equations of state are consistent with the observations and which are not. NICER has already produced measurements of several neutron star radii, generally finding values in the range of roughly 11 to 13 kilometers. These measurements have provided some of the tightest constraints yet on the equation of state. But perhaps the most revolutionary observational tool is gravitational wave astronomy. On August 17, 2017, the LIGO and Virgo gravitational wave detectors observed an event designated GW 170817. It was the first detection of gravitational waves from the merger of 2 neutron stars. This was a landmark event in astrophysics, one of the most important observations in decades. As the 2 neutron stars spiraled toward each other in the final minutes and seconds before merging, they emitted gravitational waves that carried detailed information about their masses, their spins, and crucially, how they deformed under each other's tidal gravitational fields. This tidal deformation is the key. As the 2 neutron stars approached each other, the gravitational pull of each one distorted the shape of the other, stretching it slightly, raising tidal bulges on its surface. How much the star deformed depended on how stiff or soft its interior was, which is determined by the equation of state. A stiffer equation of state means the star is more resistant to deformation and the tidal effects are smaller. A softer equation of state means the star deforms more easily and the tidal effects are larger. By measuring the gravitational wave signal precisely, physicists could extract a quantity called the tidal deformability, which directly constrained the equation of state. The results from GW 170817 ruled out the stiffest equations of state, those predicting very large neutron star radii, and were consistent with moderate equations of state predicting radii in the range of roughly 11 to 13 kilometers. Combined with the NICER measurements and the pulsar mass measurements, a picture is slowly emerging. We are narrowing down the equation of state of ultra-dense matter, the relationship between pressure and density inside a neutron star. We are beginning to constrain what the interior is actually made of. But we are not there yet. The constraints are still broad enough that multiple possibilities remain viable. Quark matter could exist in the core, or it might not. Hyperons could appear at high densities, or they might be suppressed. The equation of state could have phase transitions, sudden changes in the properties of matter at specific densities, or it could be smooth and continuous. But GW170817 gave us something beyond just constraints on the equation of state. It revealed what happens when neutron degenerate matter is released from the prison of its own gravity. When the two neutron stars collided, the merger ejected a small amount of neutron-rich material into space. This material, freed from the extreme gravitational compression that had kept it in a neutron-degenerate state, immediately began to decompress. And as it decompressed, something extraordinary happened. The neutrons, no longer trapped by degeneracy pressure, began to decay and recombine. Nuclear reactions ignited in the expanding debris, and these reactions, fueled by the extreme neutron richness of the ejected material, forged heavy elements. Gold, platinum, uranium, elements that cannot be created in ordinary stellar fusion. Elements that require the specific conditions found only in the collision of neutron stars. This process is called the R process, short for rapid neutron capture. Atomic nuclei in the expanding debris capture neutrons at a furious rate, faster than the nuclei can decay, building up heavier and heavier elements in fractions of a second. The expanding cloud of newly forged elements glowed with the radioactive decay of these freshly created atoms, producing a transient burst of light called a kilonova. Telescopes around the world detected this kilonova in the days following the gravitational wave signal, confirming for the first time that neutron star mergers are a primary source of the heaviest elements in the universe. Think about the symmetry of that. Inside a neutron star, atoms are destroyed. Gravity crushes them out of existence, erasing the periodic table and converting everything into neutron-degenerate matter. But when two neutron stars collide, and some of that matter escapes, atoms are reborn. The very material that had been stripped of its atomic identity is released into space and immediately begins rebuilding atoms, forging elements heavier than anything a star can produce through fusion. The gold in the ring on your finger, the platinum in a catalytic converter, the uranium in a nuclear reactor, much of it may have been forged in the collision of neutron stars, created from matter that had once been atoms, was crushed into a state where atoms could not exist, and was then liberated to become atoms once more. Destruction and creation, linked by the same physics, the same matter, cycling through states of existence that span the most extreme conditions the universe can produce. Future gravitational wave detections of neutron star mergers will tighten these constraints further. Next-generation detectors currently being planned, facilities with names like the Einstein Telescope in Europe and Cosmic Explorer in the United States, will be far more sensitive than current instruments. They will detect neutron star mergers at much greater distances and with much higher precision, allowing physicists to measure tidal deformabilities with unprecedented accuracy. Each new detection adds another data point, another constraint on the equation of state, another piece of the puzzle. There is also the possibility that future observations will reveal something entirely unexpected. Science has a way of doing that. Every time we develop a new way of observing the universe, we find things we did not predict. Radio astronomy led to the discovery of pulsars, which nobody had anticipated. X-ray astronomy revealed neutron stars in binary systems, accreting matter from companion stars and producing phenomena that were completely unforeseen. Gravitational wave astronomy has already delivered surprises, including events that blurred the boundary between the heaviest neutron stars and the lightest black holes, objects in the so-called mass gap between about 2 and 5 solar masses, where neither neutron stars nor black holes were expected to exist. What else might be hiding in the data? What phenomena might we discover when our instruments become sensitive enough to see them? The history of astronomy strongly suggests that the most important discoveries will be the ones nobody predicted. And this brings us to the deeper truth underlying everything we have explored tonight. A neutron star is not just an exotic object in the sky. It is a natural laboratory, a place where the universe itself conducts experiments under conditions we cannot replicate. Inside a neutron star, matter is subjected to densities, pressures, and gravitational fields that push physics to its absolute limits. The matter inside these objects tests our understanding of quantum mechanics, nuclear physics, general relativity, and particle physics simultaneously. Every observation of a neutron star is an experiment, a test of our theories under the most extreme conditions nature provides. And the central subject of that experiment is the destruction of atoms. Everything we have discussed tonight, from the architecture of the atom and the forces that hold it together, to the moment of core collapse when electrons are driven into protons and ordinary matter ceases to exist, to the new forms of matter that emerge on the other side, governed by neutron degeneracy pressure and nuclear forces and possibly exotic phases of quarks and hyperons. All of it traces back to one fundamental fact. When gravity becomes strong enough, atoms cannot survive. The atom, which has persisted for billions of years, which has endured the cores of stars and the violence of supernovae and the cold of interstellar space, which has formed every element on the periodic table and every molecule in your body, which has been the basic unit of matter since the universe cooled enough to allow its existence. That atom has a breaking point, and inside a neutron star, that breaking point is exceeded. The electromagnetic force that built the atom loses to gravity. The quantum mechanical rules that gave the atom its structure are redirected, no longer supporting atomic architecture, but instead supporting something entirely different. The matter transforms, the elements disappear, and what remains is a state of matter so dense, so extreme, and so poorly understood that it stands as one of the last great mysteries of the physical universe. We began this journey with a simple statement. Inside a neutron star, atoms cannot survive. Now you understand why. You understand what atoms require to exist. You understand the forces that hold them together and why those forces are normally so resilient. You understand how gravitational collapse can overpower those forces, how electron capture converts protons and electrons into neutrons, how neutron degeneracy pressure provides a new form of structural support, and how the interior of a neutron star is layered into regions of progressively more extreme and less understood matter. You understand that the neutron star is not simply a giant atomic nucleus, not a uniform ball of identical particles, but a complex, structured object with a crystalline crust, a pasta-filled inner crust, a superfluid core, and a mysterious inner core where matter may exist in forms we have not yet confirmed or fully described. And you understand that this is still an active frontier of science. The equation of state of dense matter remains unsolved. The composition of the inner core remains unknown. The question of whether quark matter exists in stable form inside neutron stars remains open. These are not historical questions with settled answers buried in old textbooks. They are live, urgent questions being pursued right now by physicists around the world using gravitational wave detectors, X-ray telescopes, radio observatories, nuclear physics experiments, and theoretical calculations. Every year, new data arrives. Every year, the constraints tighten. And every year, we get a little closer to understanding what matter becomes when atoms can no longer survive. The universe built atoms in the first few minutes after the Big Bang. It has spent nearly 14 billion years using those atoms to construct everything we see. Every star, every planet, every grain of dust, every living thing. But in certain places, in the collapsed cores of dead, massive stars, the universe takes those atoms apart again. It strips them of their electrons. It erases their elements. It compresses them into something new. And that something new, that neutron degenerate matter, existing under conditions of almost inconceivable extremity, remains one of the deepest puzzles nature has to offer. We are only beginning to solve it. And the answers, when they come, will tell us something fundamental not just about neutron stars, but about the nature of matter itself, about the limits of the physical laws that govern everything, and about the universe's capacity to create forms of existence that defy everything our everyday experience has taught us to expect.